right, hello again. This is Kinematics Review. This is problem number 18. So we'll solve this one together, and I have it called up here on my laptop. So I'll read the problem, and then we'll talk about the solution. So a student wishing to determine experimentally the acceleration g due to gravity has an apparatus that holds a small steel sphere above a recording plate as shown above. When the sphere is released, a timer automatically begins recording the time of fall. The timer automatically stops when the sphere strikes the recording plate. The student measures the time of fall for different values of distance d shown above and records the data in the table below. These data points are plotted on the graph. So they gave us the data points. There's 5 data points at different distances and the time it takes to fall that distance. And then they graphed that. So I sketched in what the graph looked like. This is an exponential curve. It is not linear, so you should notice that don't draw a straight linear line. Draw an exponential line. It is a square relationship. That's important to understand. It's a square relationship, not a linear relationship. So the first part is just fill in the curve and fill that in with a square relationship, not a linear relationship. You should see the dots, how the data is laid out, that it's not linear. So that's the first part. Okay, then it says a student can use these data for distance d and time t to produce a second graph from which the acceleration g due to gravity can be determined. This happens in physics often, with algebra-based physics especially. You take data, you graph the data, you find that it's not a linear relationship. So this is clearly not a linear relationship. Find a relationship that is linear, because then you can find slopes and areas and things like that. You can't find the slope of this graph. The slope is constantly changing. Unless you use calculus, which this is algebra-based class, you won't be doing that. But same thing with area. You can't find the area under that graph because it's not a straight line. It's not a triangle. So find the relationship that will make a linear relationship, or find a graph what will become a direct linear proportional relationship. Since this is a square relationship, graph distance versus time squared. So if you square all those time values for those same distances, you can make a graph and it'll be linear. So that's what we did. And let's get back. Okay. So in part B, if only variables d and t are used, what quantity should be graphed to produce a linear relationship? D versus t squared. So distance d versus t squared, square all the times in that data table, and then graph distance versus time squared. Then you get a linear relationship like this. And I just did this on the whiteboard without using graph paper. Really crude, but I got a slope of about 5 meters per second squared. So I drew a best fit straight line. 2 is the rise, go from 0, 0 to 2.4, 2 divided by 0.4, and then you get 5 meters per second squared. That is the slope. So we did label the axis, show the scale. So determine an appropriate scale, and then graph it so it fills the whole entire graph. So use the slope from part C to determine the acceleration g in this experiment. So remember this equation, one of the constant acceleration equations. Initial velocity is 0 when you're dropping something, so this drops out here. And then you get delta y is half at squared. Divide by time squared, delta y over time squared, and that's the slope, rise over run, which is the distance, or delta y over t squared, and that is equal to half of the acceleration. Our slope is 5, so 1/2 a equals 5, and a would then equals 10 meters per second squared. Just real crude graph here, but very close, and we expect 9.8, but based on the accuracy of the graph, 10, we got 1 digit, so 10 meters per second squared, pretty close. And then part E, state one way in which the student could improve the accuracy of the results if the experiment were to be performed again. Explain why this would improve accuracy. what can we do to improve the accuracy of this experiment? So one way, and this could be, you can have several different answers, and we can talk about some. But one way is more data. So there's 5 data points. Take more data, more distances, more times, drop from higher distances and go more distances to get more time. So more data would help, and you get a best fit straight line, a better best fit straight line that would help the accuracy. That's probably the first thing that comes to mind. Number 2 is we did this experiment from one of the early experiments that we did in August. We dropped baseballs and racquetballs and tennis balls from the freshman center, and that height was about 6 meters. And we used just a cell phone or a timer to really start and stop. And but how can you improve that? Maybe higher if you could do. It's in the air longer if you have a longer time. Measuring time is difficult, so maybe a longer time period, a longer distance, a longer time period, that may help the accuracy as well. More sophisticated equipment, maybe record it, and then record it, drop it as it goes down, and then you can get a measure of time better with a video recording. So those are 3 things, and there may be others as well. It did mention one, but first one comes to mind is more data, more trials. Number 2 is a higher trial, which will give you longer times. And then the third one would be to video record it, and then you can see, get a better reading of time based on that video recording. So those are 3 things. That's number 18. I don't think we've done this one in class, or we've seen this one before. So, but this is a good problem for in preparation for the exam, because I know they really like experiments and being able to analyze experiments and how to improve on experiments. So this is an experimental question. So again, if you have any questions, you can email me or post on the Edmodo website, and we can discuss those on that website. Thank you.